Machine learning is a set of data processing techniques that derive from methods in statistics and probability. Um, Possibly because of the rather mysterious sounding term machine learning. It contains both machine and learning. It's become increasingly associated with artificial intelligence. It's really kind of a data centric method that enables a lot of the things that appear to be mysterious and wondrous about what machines can do in terms of what they can understand in data. um, what I hope to do in this video is to persuade you that machine learning is not really all that mysterious. We don't really get into the truly mysterious things until we start talking about neural networks in a couple of weeks. But as far as machine learning goes, it really is just a set of techniques that come out of statistics, and it's a way of starting with a data set and having the computer understand some kind of pattern within the data. Okay, and we're going to get more into those definitions as we go along. And I'm also going to demonstrate in this video how you can, using some software that you have available to you for free as a Radford student, you can pull some data in and actually start to see how some of these machine learning algorithms work. Okay, so in this video, I want to just give an intuitive definition of what machine learning is. I know that we've had several readings now that you've probably gone through them already and got some of these definitions, but I hope to give kind of a very simple way of understanding how it works. I want to show the difference between supervised and unsupervised machine learning. I want to talk a little bit about how it is that you decide on the effectiveness of certain machine learning. There are certain one of the real fundamental tasks that machine learning is asked to do is classification, and in order to understand whether the classifiers that the machine constructs are useful for our purposes, we have to be able to understand how to evaluate them. So we'll talk a little bit about those. And then, then finally, I'm going to show you how some of these fundamental algorithms can be done in a program called SAS Jump. Specifically, we'll look at logistic regression. We'll build the little naive Bayes classifier. We'll take a look at some decision trees, and then finally do K-means clustering. Okay, so that's what we're going to do in this video. So in order to understand machine learning, I gave this example in class where I told you that my daughter is currently applying to colleges. And so we've been thinking about, well, how do admissions officers go about, deciding deciding who to admit. And so what they might do is, to put together some kind of a rating system where they say, okay, we're going to assign a rating, which, these come from experience and intuition. We just say, okay, this is how we would like to weight these various criteria of the applicants. So we just know that because this is what we feel is important and what we have seen in the past, and just basically what our experience and intuition tell us should be the breakdown. And so we assign a rating, which could be this weighted sum, right? So we have some kind of rating. We don't know what that scale is going to be because these are all at different levels of scale. But so we'll just do a weighted sum where we're doing 2 times the GPA plus 4 times maybe the quality of the letters of recommendation, 3 times the essay, 2 times the essay, plus 1 times the extracurricular. Okay, so this is how you would put together a typical ratings model. Well, if we were to go the other way, rather than deriving those weights from just human experience, we might want to use machine learning. And so with machine learning, we take some data, we've accumulated, let's say, hundreds of thousands of students over the years, and we have some way of kind of judging whether they've been successful or not. Let's just say we rate them 0 or 1 depending on some kind of threshold for quality of student. And so we go through these, we've got this data here of our historical data of our students, and we've got that target, so-called, which could be 0 or 1, successful or not successful, and we have all of these different criteria that are visible to us for applicants. And then we say to the computer, okay, now based on your own calculations, what do you think would be, what do you think would be the appropriate weights to put on these various criteria in order for us to, best be able to predict whether the student we're admitting is going to be a successful student. Okay, so the key difference in the approach is that rather than coming up with our own model for how to do this, we give the computer the data. We say, these were the successful students, these were not the successful students. Come up with some way of combining these attributes of each student in such a way that we will most often be correct in predicting whether they will be a successful student or not. Okay, so the basic feature that underlies all of these machine learning methods that we're going to talk about is that we just start with data. We feed data into the computer and we ask it to come up with some kind of pattern that we can use. Okay, some kind of classification scheme, sometimes a attribute weighting scheme, just some kind of tool that we can use that we can then look at new data and it can predict something about that new data. Okay, so instead of having a completely specified solution, we ask the computer to learn from the examples that we've given it. Okay, so for example, one of the popular applications of machine learning, and in fact, we cited this at the beginning of the course as being one of the most promising applications of artificial intelligence in general, is to take image data and to be able to automatically understand what's in it. Okay, so in this case then, if we were to take a machine learning approach to this problem, we would say, okay, well, we've got, let's say, millions of pictures. We want to be able to identify a cat. Okay, so rather than tell the computer what to look for, okay, some way of deciding that these are pointy ears and whiskers and what they look like in terms of pixel data, we just say, okay, let's get millions of pictures of cats and millions of pictures of things that are not cats, and then we just tell it, okay, there's a cat, this is not a cat. And so with the idea being that the data representation would be pixel data, right? Each little picture element on here is a certain color, and the computer would take these millions, billions, trillions of pieces of data and realize, okay, well, cat tends to have these characteristics, and the non-cats tend to not have these characteristics. So we feed that data in, and the computer comes up with some kind of model that we can then feed it a new picture, and it will tell us whether or not there's a picture, whether there's a cat in that picture. Okay, so we just had the computer come up with the model for how it knows what to find. Okay, and an example that we talked about in class where this kind of automatic image recognition computer program could come in is in safety enforcement. So we could come up with some machine learning process where we want to be able to identify when somebody is not wearing a hard hat. And we've got this camera aimed at a certain place, and it takes a picture every few seconds, and will be able to alert us if somebody's not wearing the appropriate equipment. So we could say, okay, here's how you learn, here's how you learn about hard hats. Here's a picture of people wearing a hard hat. Here's a picture of people wearing a hard hat. And here's a picture of people not wearing a hard hat. Okay, so we feed these images into the computer processes all the pixels, and it learns, what to look for. And it it comes up with some kind of model. Okay, and that's all we're going to say for now, is that it's some kind of model, some kind of way of taking the attributes of the picture and determining which ones tend to go along with the label that a hard hat is present. Now this is a kind of tricky for 3D imagery. But what we'll see later when we get into neural networks is that this is the kind of task that they just do an amazing job at. This is certain kind of neural network, a convolutional neural network, can do a task at a shocking level of accuracy, this kind of thing. But that's for another time. Okay, so um, so this kind of learning, where we have some kind of data that we're feeding in, and we are accompanying each data row or each data instance with some kind of label, and then we ask the computer to discover the relationship between the data and the label. This is what's called supervised learning. Okay, so in the supervised flavor of machine learning, we're giving labeled data to the computer, and its algorithm learns patterns. Okay, and most of the machine learning tasks are classification tasks. Okay, there are other things that they do, but for the most part, classification is the most used one. So here are, we say we got the data and the algorithm. These are some of the algorithms that are supervised machine learning. And I'm going to demonstrate some of these in a little bit. We're not going to get into a lot of the real mathematical and technical detail of these. In fact, the demonstration that I'll do later requires absolutely no programming whatsoever, and no mathematics either. Well, a little bit of mathematics, but not a whole lot. What I want you to understand is that these are the different algorithms, the supervised machine learning algorithms, and given a classification task, we would go through and maybe kind of feed our data into these and decide which one seems to work better. There's not really any way of knowing ahead of time which one might work best for our data and our classification task, and so it's often, when you're building a machine learning tool, you just have to go through and figure out which one works the best. And interestingly enough, there are cases where one might work better, but then as you get more data, another one might work better. So you have to continuously update your algorithm. Okay, so that's supervised machine learning, labeled data. There's also unsupervised machine learning, where we don't really have a target variable. We don't have some kind of thing that we're trying to get it to be good at predicting. We're just providing data to the computer and asking for it to look for patterns. Okay. Now, in this case, we don't. So it's not a classification task that's really going to be involved here. This is clustering. So the most common task for unsupervised machine learning is clustering. Okay, and we'll go into what that means. But here are some of the algorithms that are associated with the unsupervised machine learning: K-means clustering, hierarchical cluster analysis, and principal components analysis. And we're just going to look at K-means today. Okay, so backing up a little bit, this classification task. So with the classification task, as I said, we're going to be having some kind of target variable in our, for each row. Let's say, so each row we've got a student here, and we're going to add a column here, which is going to be 0 or 1 based on whether the student was successful or not. So we are going to have the computer learn the features that matter and learn how to combine them and weight them in such a way that its predictions, it can predict this 0 or 1 with a certain amount of accuracy. Okay, so the idea is, this is classification because we're going to take a row, we're going to take a new row, we're going to feed it through our classifier, for example, our logistic regression classifier, and it's going to output a 0 or a 1 based on whether it thinks this new data is more similar to the historical zeros or the historical ones. Okay, so there's an example of a binary outcome classification task. It's not the only task. It's not the only kind of classification. We could have what's called a multinomial classification. Now, even though I have a picture of the same data here, just pretend that this is actually different data. And what we want to do is like maybe say this is information about the doors that people go through at certain times. And let's say we have a classifier that has gone through historical data and tries to identify maybe suspicious behavior. And so the classifier in this case would have, 3 different possible labels for each row. So we'll go through the historical data and then label something as a high-level threat, a low-level threat, or no threat, and have the classifier learn the characteristics of the data that go along with each, so that when we deploy that classifier, we just feed the new data into it and it can just classify that row as one of these 3. Okay, so that's what we're going to do. The classification task is very fundamental, very important one, possibly the main one in supervised machine learning. And so we can always make a classifier, but we're always concerned with how good of a classifier it is. So when we make these classifiers in a minute, we're going to have to take a look at some of the output from the software to decide, well, I mean, how good of a job did it really do? So, for example, in the case of the students, the applicants, the student applicants, if it can only predict that 0 or 1 50% of the time, then that's not really a very good classifier. That's no better than flipping a coin. So it's hardly worth the trouble of even going through the data in that case. So after we make a classifier, we need to make sure that the classifier does a good job. Okay, so here's how we're gonna judge these classifiers. So in evaluating the performance, then is accuracy going to be enough? So we just say, okay, the percentage that we got right. But that doesn't really work because, for example, what would happen if we had a data set with 99% zeros and 1% ones? The classifier would just always say 0. And it would always guess 0. And it would be correct 99% of the time. So accuracy doesn't really tell us the whole story, right? It would be missing the rare 1% of the ones that are probably the target of what we're interested in anyway. So we can't really use accuracy. Accuracy is not a good measure. So for an example, let's say that 1 indicates that this customer has purchased our product, and 0 indicates that the customer did not purchase our product. So there are 4 different cases that we need to take into consideration with the binary outcome. Okay, so we've done our classification, and then how do we know how good of a job the automatic classifier did? Okay, so there's 4 different cases here where we classify it as a 1. Okay, so they bought it, and it actually is a 1. Okay, so we know what the true outcome is because we have the historical data, but then we hide that and then see how well the classifier does and see if it predicted it correctly. So we classify as 1, and it's actually 1, so that's a true positive. Okay, we classify as 1, and it's actually 0. There's a false positive. We classify as 0, and it's actually 0, so that's a true negative. And we classify as 0, and it's actually 1, so false negative. So in 2 of these cases, so in this case, we got the right answer, so that's true. And then in this case, it's, we got the wrong answer. Okay, sometimes we could get it wrong by saying, 1, sometimes we get it wrong by saying 0. So we have a nice visual way of consolidating these 4 cases into one nice little chart. Okay, and this is called the confusion matrix. Okay, and we'll see some of these in action in a minute when we start to actually make these classifiers. So the confusion matrix summarizes on one axis, and I've seen it. Sometimes I've seen these axes reversed. So be aware where they put the predicted and where they put the actual. Okay, so in this case, we put the what our classifier predicted would be the outcome for this particular row. And on this axis, we have what the truth was. Okay, so here we have this case where it was actually a 1, and we predicted that it was a 1, and so we have a true positive. If it was actually 0, and we predicted 1, then we got that wrong, and that's a false positive. Okay, and likewise, so over here, we predicted 0, but the truth was 1, so that's a false negative. And here we're predicting 0, and it is 0, so that's a true negative. So what you want to see in your confusion matrices is you want to see a lot of true positives and a lot of true negatives. So this major axis right here, you want to make sure that those are high, and then you want to make sure that these over here are low. Okay, and if there is some kind of strange patterns where, like, okay, I'm generally pretty right, except I have a lot of false positives, then that says something about your classifier, and maybe there are certain cases where it shouldn't be applied. Okay, so there are a few metrics that we can use to further quantify the quality of the classifier using this confusion matrix. Okay, so there's something called precision, which refers to, you can just think of this as, okay, you've grabbed a bunch of the rows and then identified all of the ones, and you might be interested in, well, what's the percentage of the ones that I predicted were positives were in fact positives? Okay, so if you only identify one thing as positive and it is positive, then you have a precision of 100%. Okay, but obviously that's not the whole story, right? Because contrary-wise, if we say that everything is a 1, we are going to have a very low precision, right? Because you're going to have you'll have true positives, but you're also going to have an awful lot of false positives because they're all positives. Okay, so precision is a way of summarizing, well, how accurate is the ones that you identified as being positive, how many of those are actually positive? Okay, so if you think about this example of only picking one and saying it's 1, you have a precision of 100%. But what's called your recall is going to be very low. So the recall refers to the percentage of actual positives that you've predicted as positive. So this is going to be true positives divided by true positives plus false negatives. Okay, so in general, this says how many of the ones did you find, okay, in the whole set. Okay, so let's say there's 100 ones and you only found 50 of them, then you have a 50% recall. Okay. All right, so in general, what happens with precision and recall is as precision goes up, recall tends to go down, okay, and vice versa, of course. So you want to find some kind of nice balance between precision and recall. So there's this metric called F1, and this is really just some kind of mean. It's like an average, a strange average of precision and recall. So generally, F1 will kind of summarize the trade-off of precision and recall. Okay, so you want to try to get as high precision as you can and as high recall as you can, and so thus the high F1. Okay, so another metric that I've seen being used more and more is just what's called the misclassification rate, and we will see this when we actually try a classifier in a minute. This misclassification rate just answers how often is it wrong. So you see, it's just all the times that you were wrong, that is either with a false negative or a false positive, divided by everything. Okay, the total number of predictions. Okay, so what percentage of your predictions were wrong in either way? Okay, so that's kind of a useful one also. Okay, so obviously I can't require this, but if you would like to go ahead and pause the video and take a look at this. This is a confusion matrix here. Notice that the axes are reversed, as they sometimes are. So here they have the predicted values up here, and they're yes and no's, and the actual values down here. So that would mean that if they actually are yes, and we predicted yes, then these are the true positives down in the lower right corner. Okay, so um, uh, I encourage you to, at this point, go ahead and pause the video and calculate the precision and the recall and the F1 for this confusion matrix. Okay, so we can, so this is the result of some kind of classifier. We've made this classifier. It tried its hand on existing data, and this is what it came up with. That 100 for of the 165 they tried, 100 of those we predicted yes, and they were actually yes. Okay, and we 50 of those we predicted no, and it was actually no. And so we see that this left-right axis here is most of them, so we can say that's a pretty good classifier. But we have twice as many. So let's see, if there's actually no, we predicted yes, that would be false positive. We have twice as many false positives as we have false negatives. Okay, so I'm not going to post the answers. I think the mathematics is fairly simple, but before you go on, go ahead and try your hand at calculating precision, recall, and F1. Okay, so with the next part of this video, I want to go ahead and get into the actual, I want to get into actually taking a look at, trying our hand at making a classifier using some tools that are commercially available, not terribly out of reach cost-wise, and in fact, this one is free to you as Radford students. So if you want to follow along, the tool that I'm using is SAS Jump, JMP, and it's not the full SAS language with the whole enterprise infrastructure and everything. It's just a point-and-click statistics tool that uses, it can optionally hook into a more powerful SAS underlying base, but it's kind of a nice simple tool to use for a lot of statistical things. In fact, it's what I usually use when I'm doing research. So you can either just go to the SAS Jump webpage, and they have a 30-day trial version. Or if you go to IT One Stop at Radford and just search for SAS Jump, it'll lead you to some instructions. So basically, I think you may be able to request your own copy of this. In fact, if you're interested, I'll talk about getting licenses for all of you. But you can use the virtual lab, which means that you will remote desktop to a computer on the Radford campus and use the software that's on that. But either way, if you really want to get a copy of Jump, come and talk to me, and I'll look at, if necessary, just getting some department funds to get you a copy. Okay, so I'm going to be using SAS Jump, and these are the data files that I'm going to be using. I've uploaded these into the machine learning module section of D2L. There's something called, they're all in the form of Excel spreadsheets. We got churn data, Iris, and Titanic. Okay, so this churn data is just a small data set that I've made. This Iris data set this is sort of like the hello world of machine learning. I've seen this Iris data set over and over again in lots of different contexts, and it's just a very nice starting data set to use. And I think this is actually a data set that came from passengers on the Titanic, and we're going to see if we can write a classifier for those to understand something about that journey. Okay, so as I said, we have several different supervised machine learning algorithms. Again, we provide the computer a label, and it learns how to combine the attributes to give the most accurate classification it can. Okay, so the first one is a logistic regression. So let's go ahead and start with the churn data. I'll just demonstrate this real quick in Excel. So this data has just 4 columns. It's got a customer ID, the number of calls that that the customer has made to the help desk. This is the number of years with the company, and this is what's called a churn code. So churn means that they have canceled our service. So what we're trying to do is understand how these two columns, the calls and the years, lead to a customer to abandon our service. Okay, and it looks like we've got around 30 observations here. We've got a bunch of ones, a bunch of zeros there. We could do a pivot table if we want to understand more, but we don't need that right now. Okay, so we're gonna go ahead and do a logistic regression where we're going to predict this 1 versus this 0 using these as independent variables. Okay, and I have a video on D2L on logistic regression, and if this is not something that you're familiar with, you can go ahead and take a look at that, and it should clarify some of this. But a logistic regression is just going to give us a probability that somebody is going to be a 1 given these two pieces of information. Okay, so this is a logistic regression. Now, it actually outputs something called log odds, but that can easily be converted into a probability. It's just a formula that you can plug in. But the log odds, if we take the regression coefficients and combine them, we're going to get some kind of thing that we can call a probability that a customer is going to churn. Okay, so this is, basic form of learning. Okay, it's going to learn the weights to put on these two attributes. So let's go ahead and see what it does. Okay, I got my churn data right there. Oh, and incidentally, if you're following along, to open up a new data set, you just got to go to File and Open, and just browse to the data that you downloaded, and it should just import fairly cleanly. These are not real messy data sets. Okay, so there's our data. All right, so in order to do my logistic regression classifier, I can do Analyze, Fit Model. Okay, well, actually, first of all, let me make sure the data is the right type. So this churn code, this is nominal data. Okay, it's not continuous, and it's not discrete. It's just nominal data. It's not even ordinal. So we're going to come to right-click on it, column info, and I'm just going to make sure that this modeling type says nominal. Okay, so it's nominal data. And now, once again, I do Analyze, Fit Model. Okay, so this dialog here lets you set up a regression where you can put your dependent variable there. That's our y. Okay, so we want to predict churn on the basis of calls and years. So I'll hold down Shift and select both of those, and I'll add these down here. Okay, so this is where our y goes, and this automatically changes to nominal logistic. Okay, and we have our independent variables here. Okay, and my target level, I'm really interested in what makes somebody a 1. So how do these cause a customer to churn? Okay, so now when I click this run, the learning begins. Okay, and it gives me this output. Okay, and so what it's done, so remember in the first example where I said, okay, well, what if we gave this historical student data, and then it came up with some way of coming up with a weighted sum of all these different variables? Well, that's exactly what it did. Those are down here under this parameter estimates. So I'm not going to go into exactly how to interpret these coefficients right now, but let me see if I can zoom in a little bit. I cannot. Let me see. Okay. All right, there we go. That's a little bit easier to read. Okay, so down here, these parameter estimates tell us something about the relationship between calls and years. So the estimate here, so this is positive, right? So it's 0.07. And if I look over here, this just tells me that this is significant. So we know that the number of calls contributes significantly to whether somebody is a 0 or a 1. And we know that the number of years is also significant because this is less than 0.05, okay? And I'll notice that the calls is positive, okay? So therefore, the number of calls that somebody makes has a positive relationship to their probability of being a 1, right? Remember, 1 means that they've left, so more calls means greater likelihood of quitting, okay? And I see that years, the coefficient is negative, 0.84, so its magnitude is stronger here. Well, okay, so but the years is smaller on a smaller scale, but we see that this is negative, so that means the number of years with the company, as that goes up, it decreases the likelihood that they're going to quit. Okay, so we've just done machine learning. Okay, so this is the logistic regression is kind of the entry point of supervised machine learning. Okay, so we've come up with a classifier here that tells us the log odds, which we can convert to a probability of this customer churning. Okay. All right, and there's a lot more in there, but well, let's take a look actually. So as I said, a classifier, we judge it with the confusion matrix, right? So let's go ahead and take a look at the confusion matrix. Okay, how often was it right versus wrong? And so I've got that down there. You can see. Okay, so now we've got predicted on this axis and we've got actual over here. So this would mean that when it was a 1 and 13 times it was a 1 and we predicted 1, and 12 times it was a 0 and we predicted 0. Okay, so we can use this to classify, to come up with precision and recall metrics for this. But I can eyeball it and say that this major diagonal here is much larger than this diagonal here. So I think we can be pleased with the accuracy of our classifier. Okay, all right, so that's classification algorithm number 1. That's logistic regression, how that used. As I said, there's more detail in the logistic regression video in terms of what the magnitude of those coefficients mean, but for our context, for this context here, it's just important to know that this is a form of classification, which is a form of supervised machine learning. Okay, all right, so another classifier, another way that we can classify, in fact, I think we'll use the same data set, is to make what's called a naive Bayes classifier. So a naive Bayes classifier does the same exact thing as a logistic regression, where it comes up with a way for you to take a new data row and classify it as a 0 or a 1 in our case. It's just a slightly different algorithm. And we'll see in Jump that it's, coming up with the naive Bayes classifier is very similar to doing the logistic regression. But very quickly, for those of you who are curious, the way this works is it's an application of Bayes' rule, which comes from probability. The idea here is that we apply Bayes' formula because what we want to get to is the probability of a class given certain x attributes. Okay, so this x is actually a vector. This is all the features. So the probability that the customer is a 1 given these set of x attributes, so calls and years. Okay, so in order to come up with this, which is called the posterior, we need to be able to come up with these here. Now, we ignore this because we don't, this is going to be the same. It doesn't depend on the class, so it's going to be the same for all classes. This up here is the likelihood. So this is saying, okay, well, in the past, what is the probability of certain x variable features given the class? Okay, so in the past, this class has had what sorts of x variables, and we can get that from historical data. And then we also need the prior class probability. That is, how often does this class occur? So remember in our 99% versus 1%, if this class only occurs 1% of the time, then this class probability is going to be 0.01. Okay, so you see that for each class, we need 2 probabilities. And when we take in a new piece of data, so we put in a new row, what the classifier does is it goes through and finds out for each class, that is, in our case, there's only two classes, 0 and 1, what is the probability of it being in that class? So if it says it's 0.8, 0, and 0.2, 1, it's most likely a 0, okay? So it uses this formula and previous data to come up with a way of deciding the probability for each class, okay? And so let's see that in action using our same data set. So I'm going to come back here to Jump, same data set. I'm going to go to Analyze, and okay, just 1 second. Okay, so let's take this same data that we used. We analyzed this data with a logistic regression before. Now let's go ahead and try a naive Bayes classifier. So that's going to be here under predictive modeling and naive Bayes. Okay, so again, same kind of structure. We're trying to predict the churn code given calls and years. Okay, and so we'll make those our X. Okay, so once again, we're just putting in the target, we're putting in the variables and saying, come up with the relationship between these. Okay, I'll click OK. All right, and so it gives me a couple of metrics for the classifier. Now, if I want to actually use this classifier, I have to do more than just what I did with the logistic regression. I have to actually let's see, I can save the that's right. I can publish the probability formulas, and I can actually generate Python code here. Okay, so see, I actually generated this Python code that has the classifier actually in it, so I could use this. But for right now, I just want to know, well, how well did this work? And so notice that I have a 27% misclassification rate. And once again, it gave me this confusion matrix right here, and with the predicted and actual. And I do see that this it does appear to be right more than it's wrong. But it looks like the naive Bayes did not work as well as the logistic regression. And we would have to calculate precision and recall for each of those to see for sure. But it doesn't look to me like the naive Bayes worked as well. Okay, but so the naive Bayes is another option for a supervised classifier. Okay, that it's an application of Bayes' rule. Okay, all right. So let's see. So the third one, and this is the last classifier that I'm really going to show, is what's it's called a decision tree, where instead of coming up with probabilities of classes or coming up with regression coefficients, it comes up with a way to create a way of splitting the data one variable at a time. So like this. So let's say we had some kind of we were trying to decide on like which apartment to put somebody in, right? So we would like to have some kind of procedure in place where we make a series of decisions like this, where we ask, okay, well, is the number of family members greater than 3? And if yes, then we want to know, well, are they married? And then if yes, put them there. If no, ask if their salary is greater than 40,000, and if yes, put them there. If no, put them there. Okay, and so you can go down the tree either way, but the idea is that at each stage of the tree, you are asking the question, asking a question about one variable. So so number of family members is one column variable, right? Salary is one column variable, and married, yes or no, is one column variable. So we are basically taking the data and splitting it one variable at a time. Okay, and let's go ahead and see that in action with our churn data. Okay, so we have two different classifiers that we've made for this data now. Let's go ahead and try a third one. This time I'm going to do analyze, predictive modeling, and call it a partition. Now you see that the method here is decision tree, so we're making a decision tree, but Jump just calls it a partition. So just like before, we are trying to predict the churn code on the basis of calls and years. So I'll put those in as my X's. Okay. And okay, and so we'll go on to the next step here. Okay. Now this interface I find to be quite confusing, so I'm going to not show the points. Okay, so what this is, what this rather bizarre picture here is showing me is, so right now these are all of my rows, and I haven't done any splitting yet. And it looks like I have half of them are zeros, so the reds are zeros, and half of them are ones. Okay, the ones are blue. And if you look at this, so this is a node of the tree right here. Okay, so it looks like these are demonstrating the proportion of yeses and nos in there. So I've got half ones and half zeros. Okay, so what I do is I create this tree by splitting. Okay, I take this node, which has 30 rows in it, and just split it. Okay, so it looks like it learned, okay, this is the machine learning part of it, it learned that the way to split it is on whether calls is greater than or equal to 50. Okay, so when it's split, so we had 30 rows here, we split on whether calls is greater than or equal to 50. Now we have 8 in here, and notice that every single one of them is 1. It's blue. So this node consists entirely of rows that are customers who have left. Okay, so it said that the machine has decided that this is the most important variable, and if you split on greater than or equal to 50, then everybody over here is a guaranteed churn. Okay, so over here, notice we have a little bit more of a mix. Some of these left, but not all of them. So we might want to split some more, split again. Okay, so these over here now, so calls less than or equal to 50. We've got 22 rows here. Now it's going to split on years with the company, okay, which is our only other variable, so we don't have any more options. So it says, okay, if the years is less than 5, then it looks like most of these are ones. Okay, but if years is greater than or equal to 5, then most of these are zeros. Okay, so the beauty of a decision tree is, in addition to just it discovering statistically where the great dividing points are, a decision tree is a very usable kind of machine learning technique, because you have this this nice output that has explanatory power. You can put this in front of a person and they can actually understand how it works, and they can use this to make their decisions about identifying these people with calls greater than 50, because they're very, very likely to churn. Or if they have less than 50 but they have less than 5 years, they're very likely to churn too. Okay, so a decision tree is the most user-friendly of these. Let's see, will this give us a confusion matrix at this point? Oh, yes. Well, it gives us an ROC curve, but I thought there was a confusion matrix under there. Let's see. Okay, well, more on that to come. Okay, so there's a decision tree. I would like very quickly to show you an interesting decision tree that kind of illustrates another use for these things. So we have some models that are used for predicting. So for example, in our churn data, we really want to have that classifier, because we would like to take new data and then be able to predict either on the basis of a probability or a decision tree. We want to identify those ones who are likely to quit. So that's a model that's made strictly for predicting. But there's another use for models, and that's for explaining. We don't need to predict who's going to die on the Titanic. We already know. But we might use a decision tree to understand something about who did die. Now, I'm going to run this through really quickly because this is just kind of something kind of fun. Let's see. If you're in Jump, it actually comes with the Titanic data. I've also put it on D2L, but on Jump, if you go to Help Sample Data Library, it's got a bunch of files here. Let's see, Titanic. Yeah, Titanic. Here we go. We open this. We've got our Titanic data. Titanic passengers. Sorry, Titanic passengers. Okay, so we've got all the passengers on the Titanic here. Looks like 1,300, and we've got whether they survived or not. So there's an opportunity for a classifier, right? Classify yes or no. Find the variables that classify the row in one class or the other. And we've got what their ticket number was, how much they paid for their ticket, which lifeboat they were in, et cetera, and so on. So I'm going to make a decision tree so that I can understand what happened on the Titanic. Predictive modeling, again, partition, and I'm going to predict the nominal response survived. And I want to see, let's do which class they were in, their sex, and their age. And how about fare, what they paid for their ticket. Okay, and again, I've got decision tree selected down here, so let's build a decision tree here. All right, and so once again, I'm gonna get rid of the points because I don't like to look at all those points. Okay, so here we see something slightly different about this data. Most of the people did not survive, so we have a lot more red here than blue. So we see in the initial node, we've got mostly red, 1,309 rows, mostly red, some blue. Let's go ahead and split, okay? And it looks like splitting on the variable of sex gives us the most information gain here. So if they are female, so there were 466, most of those survived. Most of those are yeses, and most of the males did not survive. So most of those are no. So we can split again. Okay, now we see the next most informative thing to split on is their class. Okay, so if the class is first or second class, pretty much all of them survived. So basically, if you were female and in first or second class, you very, very likely survived. But in third class, your chances were only 50-50 if you were female. Okay, so we can split again. Okay, so this time the male node split. And here, this is kind of a nice thing to observe. If your age was less than 10, a much greater portion of those are blue, that is surviving, than red, whereas the males who are over than 10 are much more likely to have died. Okay, so here's an example of using a decision tree to rather explain something that happened rather than to try to predict. Okay. All right, so that's the last of our classifiers that I'm going to show you. So again, these are all different versions of machine learning, supervised machine learning, where we're trying to predict a class. We looked at a logistic regression, naive Bayes, and decision tree. These are all things that you can do in Jump, and you might just if you're there with this data set, just poke around and see if you can. You basically do them the same way. There are a couple of tricks, though, with the data. But as far as I want to show you at least one unsupervised machine learning method. So remember that in unsupervised machine learning, we're just giving data And then we don't have a target, we don't have a response variable. We're just asking the computer to find some sensible way of grouping the rows. Do they seem to group themselves together? And so in this case, then what, the obvious application for this would be like in market segmentation, where you can take your entire population here and then just throw it into the computer and say, okay, do these people tend to cluster in any kind of sensible way on the basis of these variables that I give you? So, before you apply your clustering algorithm, and K-means is just a particular way of finding these clusters. I don't think we need to step through the actual way it does it, but the idea is that you're starting with a data set that's just that consists of individuals. And then after you do your clustering, it identifies that which of these K clusters the individual is in. Okay, and so let me show you where that is in Jump. Let's see, what should we use? Oh, okay. I'm going to open up the iris data set. So as I said, this is kind of a rite of passage in machine learning. This one, I think this was collected in like the 1970s or something, so it's been around for a while. So what somebody did was they collected some data on the measurements of certain species of irises, a certain kind of flower. So apparently these species, there are 3 species. There's Setosa, versicolor, and virginica. Okay, so we've got 3 different species, and so they collected, what have we got, 150 rows, so 150 different flowers. They took the length of the sepal, the width of the sepal, the length of the petal, and the width of the petal. And the question is, okay, well, on the basis of these, could we take a new flower measurements and decide what species it's in? Okay, and if so, how do we combine these, and how do we weight them? So we're gonna revisit this data set again in the future, but I want to just show you how K-means will work with a data set like this. Now, I'm going to pretend that I don't have this, that I don't know the species, and that all I have are these four columns right here. And I'm going to ask the computer, okay, well, let's just say I just had all these measurements, and I wanted to know, well, how many species are in here? Do these seem to cluster into some kind of sensible groups? And if I come here to analyze, and let's see, I think, yeah, here's, no, wait, it's clustering, under clustering. Okay, K means cluster. Okay, so I'm just going to take these 4. So on the basis of just these 4, apply a K-means clustering and go ahead and cluster. Okay, and I'm going to take a wild guess and say do 3. So you have to put in 3, or you could put in 4 if you think that's right, or 5 or whatever. But if I say I think these should cluster into about 3 different clusters, I'll just say go. Okay, and what it gives me here is for each cluster, it has found those 3 clusters, and for each cluster, it found the average length width of each of the sepal length, sepal width, petal length, petal width for each of those clusters. Okay, and if you want to visualize it, you can come here and come to biplot. And so here's what it did. It found, these are principal components. Don't worry about what those are, but basically, combined attributes. And it found out that, okay, these all have similar measurements. These all have similar measurements, and these all have similar measurements. And as it turns out, these are one of the 3 species. These are one of the 3 species. And these are one of the 3 species. Okay. So again, this is these unsupervised methods like these clusterings, I find them to be difficult and not terribly useful most of the time. You don't get great results, but sometimes this is all you have. If you don't have labeled data, you can't do a supervised method, so you're kind of just stuck with what you can do. Okay, so that's unsupervised machine learning. Okay, so I realize that I talked a long time, but here's kind of the summary of what I hoped you got out of this long-winded ramble. First of all, so machine learning requires extensive labeled data, which is sometimes expensive to obtain. So sometimes they try to use a combination of supervised and unsupervised, where they call it semi-supervised. And sometimes you just kind of do unsupervised clustering just because it's all you could do. So supervised learning is usually some sort of a classification. So lots of applications. In fact, the substance of our talk on Wednesday will have to do with applications of classification, including, for email, spam versus non-spam, for financial data, fraud versus non-fraud, and for marketing data, potential customers versus non-potential customers. Okay. And there again, unsupervised learning is usually some sort of clustering. So when you want to lump customers, orders, transactions, or systems into a certain number of categories. Okay. And then when you have a new one, you can, based on those characteristics, put it into a cluster and be able to understand something about the cluster. Okay. Next, effective machine learning requires a large amount of data, which is often now available. One of the reasons for the big interest in machine learning is because there is a lot of data available now. I think especially in the area of imagery, I don't think it would have been easy for a common person to come up with 1 million pictures of cats. But now with the internet, that's not very hard anymore. So and anytime you can get a large number of images, you can train an algorithm. It's only a little bit more difficult than what we did to start to learn what characteristics go along with that label. Okay, so and here's an interesting one. It may be impossible to know ahead of time which algorithm, like of the ones that we saw, will work best for a given task. So sometimes logistic regression is going to be your best classifier. Sometimes, naive Bayes. It really just depends on the task. It depends on the data. It depends on the range of your data. Depends on a lot of things, and you can't really know ahead of time. Okay, and also you can't even know ahead of time which attributes are the most useful. It might be that for years you've been interested in, let's say, a person's age when deciding their creditworthiness, and you find out after you do your logistic regression that the age has no impact whatsoever on their ability to repay. I don't know if that's true, but that's the kind of thing that can be discovered by doing an analysis like this. Okay, and finally, and I hope I demonstrated this, and I hope that you will give some of these a try, that the basic learning models can be quickly and easily created using commercial software such as SAS Enterprise Miner or SAS Jump. And you can actually do more advanced machine learning with R or Python, okay? And a lot of times you can just put in something like basic supervised classifier Python and just get a little snippet of code that you can just start off with right away. Usually that Iris dataset is the one that they use for tutorial purposes. Okay. All right. Hope this helps, and good luck, and let me know if you have any questions.